Practice problems. So the linkage practice problems. The third one has, I guess, just 3 bodies. And someone told me that I don't even have solutions up for that one. So what I'm going to do is I'm going to, today, like after class, I'll replace that with another one with 2 bodies. Because first of all, like on a test, we don't have time to do one with 3 bodies anyways. And I'll get the solution to that up as fast as I can, hopefully right after class too. So no, I guess I don't have it. I don't know. Someone told me it's not up, and if it's not up, I don't have it. So, so I'll replace number 3 and provide a solution. You can also, go through those example problems. You can think of those as more practice problems and compare your work and your answers to what I got in class. So yeah, I think the linkage part of the test is going to be, it's going to be 1 problem with 2 members. Like my hand is sort of forced on that one. There's no time for more than 1 problem, and there's no time for more than 2 members. So all I can do is change the configuration of it, A 1-member linkage connected to another member by a fixed joint in the middle. I'm not going to do that, but I could do that. All right, and so then, 2 or 3 questions on rigid bodies, 1 question on linkages. That's the test. That's, the 2 tests really, but what you'll be doing at the test time tomorrow. Any questions about the test day tomorrow? So, not yet, but I'm going to. So tonight, I don't know if, I'd have to guess they're not going to be graded by the test. I know that would be ideal, but I kind of don't think they will, but I'll try. But so what I would say is you have to understand, you have to be ready for rigid bodies for the final anyways. Come here, take the test on rigid bodies. I'll grade both of them. I'll take your higher score, So in summary, I'd like to say things, in my opinion, got a little shaky for about 3 days. We're back on track. Let's nobody freak out. Okay. So, and then I'll have everything graded by the end of the day Friday, so you'll know what you have to, yeah, right. So you'll have plenty of time to study for a makeup on Monday. And yeah.
The finals on Thursday or Friday?
Thursday. Yep, and we're done. That's the end of the class. Yep, there's nothing on Friday. All right. So now we're going on to my favorite stuff in this class, the most interesting stuff to me. Yes. So yeah, we'll have lecture on Tuesday and Wednesday. Some of that will be finishing up non-inertial coordinate systems, and then some of that will be just a little bit of stuff on energy, on the work energy principle, how to use that in dynamics with rigid bodies and stuff. And then, you can bring questions and stuff too. Okay, so back to particle kinematics and kinetics in non-inertial coordinate systems. Okay, and remember that there are 2 ways to have non-inertial coordinate systems. The first one is an accelerating origin, And the second one is rotating coordinate system axes. I'm not really going to say much about this, although this will come up in a couple problems that I'll do today and Tuesday. But this just has to do with using the relative motion equations. This one's a little trickier, and this is the one that I'm focusing on. So we're dealing with how to do calculations when your coordinate system, so when all your measurements are in a coordinate system whose axes are rotating. And last time I gave you this result. I'm not going to prove this or anything. You can actually, if you think of it in polar coordinates, you can do a proof of this in polar coordinates. That's not a general proof, but at least it can sort of help you, believe that this is true. But I said that in a rotating coordinate system, any vector u, if you take the dot product of it, not the dot product, take the time derivative, so u dot is equal to the time derivative of the components plus capital omega crossed with u. And this term is the observed u dot, okay? This is like if all you had were measurements in your rotating coordinate system, this is what you would think the time derivative is. And this is the unobserved correction term. And this capital omega is the angular velocity of the coordinate system. So one thing I guess that you need to keep in mind is none of this does you any good if you don't know. So what if you know that your coordinate system's accelerating, rotating, but you don't know anything about how it's accelerating or rotating? These don't do you any good. You need to know what the rotation of the axes is like. Okay, that's what this capital omega is. Okay, so now let's apply this to, our main interest in this. So this is true of general vectors, but our main interest is we want to know how to calculate velocity vectors and acceleration vectors if the coordinate system is rotating. So now we're going to apply this to a position vector to get velocity and acceleration in a rotating coordinate system. All right, well, the velocity is equal to the time derivative of the position vector. And that means that, so in a rotating coordinate system, time derivative of p is time derivatives of the components of p plus that correction term, capital omega crossed with p. So this term, how would you describe this in words? That is the observed velocity. That's what the velocity looks like to the person in that rotating coordinate system.
And then capital omega is what an outside observer would see the coordinate system.
Right. That's right. And so now what are we going to do to get the acceleration? Well, we've come this far. We might as well just keep applying this to the velocity. So now the acceleration, the acceleration vector is equal to velocity dot, okay? And so you can think of that as, so that is the derivatives of the components of this plus that correction term. Okay, so how do you take the derivatives of the components of all this? Well, first take the derivatives of the components here. What do you get if you take the derivatives of these components? Double dots, yep. So px double dot, py double dot, pz double dot. Now, what about this stuff?
So it's omega prime, derivative of
Yep.
omega cross p plus
Yep.
log omega cross p dot.
Omega cross, yeah, the time derivatives of the components. Yep, that's exactly right. And that's just because of the product rule. Okay. So plus omega dot cross p plus omega crossed with derivatives of the components. Okay, but that's only the this is without the correction term. So now we have to add that to omega crossed with our original velocity vector, this thing, all of this. So px dot py dot pz dot plus omega cross p. So now let's just simplify this. So A is equal to, so notice that, well, so first we have px double dot, py double dot, pz double dot. And then we have, I'll add this term in, omega dot cross p. Now, if you distribute this omega cross through that second set of brackets, you have an omega cross derivatives of the components. We have another one of those here, so we get 2 omega cross components dotted. And yeah, that's right. And then, I mean, you can do it, that 2 will distribute through wherever you want. You can apply it at any point in that multiplication. And then the last thing is omega crossed with omega cross p. So there's the acceleration. It's kind of a mess. So let's think about what some of these terms mean. So this one, how would you describe this in words? That's the observed acceleration. That's right, in the rotated coordinate system. This one is the, we've already talked about this one. This is the observed velocity What's this omega dot? That's right, that's the angular acceleration of the coordinate system. Why don't we call it, so if we call the angular velocity capital omega, why not call this capital alpha? The best I can figure is because capital alpha is just a capital A, and so it doesn't look Greek anymore. So for some reason, people don't call it that, but that would be reasonable, you know. So this is the angular acceleration of the coordinate system. And then this last term, maybe you've heard this term mentioned before. This is called the Coriolis acceleration. The Coriolis acceleration, the Coriolis effect, if you've heard of, so basically, like, we almost always treat the Earth like it's an inertial coordinate system, right? But for very sensitive calculations, the fact that the Earth is rotating much slower than that, you know. I mean, like, it's rotating really, really slowly if you think of it in terms of like an angular velocity. It's rotating 360 degrees, or it's rotating 2 pi radians every 24 hours. So that's a tiny omega, you know. Yeah, I mean, there are a lot of applications where you need to take that into account. And somewhere in France, there's this big, super long pendulum called the Foucault pendulum that, you know, like a pendulum under the influence of gravity, if it's in an inertial coordinate system, it just goes back and forth in a plane, right? But since the Earth is slightly non-inertial, the coordinate axes are rotating, very slowly you see the plane that it's in rotate. Maybe it does it every 24 hours. That would make sense if it goes through a full rotation every 24 hours. But anyways, that rotation is from this Coriolis effect.
Do you know if you could turn off?
Yep. Okay, so I want to bring up some things to keep in mind about this. So notice, so first, oh, and you know what? Actually, don't write it like that. Erase that. There won't be any residue because it's electronic. So compare these two, because we have these two equations that look sort of similar in a lot of ways. We have the acceleration is equal to alpha cross r plus omega cross omega cross r. And then we have the acceleration is equal to p double dot components plus omega dot cross p plus 2 omega cross components dot plus omega cross p. Okay, so notice that this term and this term are basically the same thing. And notice that this term and this term are basically the same thing. And you have, in our new acceleration, you have these two that don't appear. There's no analog in the other one. But so I want to just kind of compare these things. So first of all, if you're talking about, so lowercase omega versus uppercase omega, what does lowercase omega represent? Angular velocity of what? Like they both represent angular velocities. This one, so lowercase omega represents the angular velocity of a rigid body or circular motion in an inertial coordinate system. So I'll say angular velocity of a rigid body in an inertial coordinate system. Uppercase omega is the angular velocity of a rotating coordinate system. And so same thing with, so number 2, alpha versus capital omega dot. Alpha is the angular acceleration of a rigid body in an inertial coordinate system. Capital omega dot is the angular acceleration of a rigid body. No, that's the whole point, is not to say that. Omega dot is the angular acceleration of a rotating coordinate system. Number 3, R versus P. Okay, so notice in the rigid body equation here, we're doing our cross products with this vector R, and with the rotating coordinate system equation, we're doing our cross products with the vector P. So what are the differences there? Well, what's the R vector? So that it's of a rigid body, but it's not necessarily a position vector. That is, So this is a, yeah, right. It's a vector from the center of rotation of a rigid body sometimes that's a fixed point, sometimes that's the center of mass. I'm missing half of this sentence. To the desired point. So for that to be equal to a position vector, the origin would have to be at the center of rotation. Okay, sometimes that's true, but it doesn't have to be. P is actually a position vector. So that's a vector from the origin to the desired point. What? Yeah, oh, it's so rich with quiz questions. Apparent position, velocity, and acceleration in a rotating coordinate system. Okay, so components dot and components double dot are the apparent velocity and acceleration vectors, respectively, to an observer in a rotating coordinate system. Okay. And actually, like if you talk to, so you're talking on the phone to someone in a rotating coordinate system, and so they don't give you positions that you can take derivatives of or whatever. Say they just report to you what like, here's what I see. I see an acceleration like this and a velocity like this. You could use this equation to back out, I mean, you could just plug in what they report to you here and here to come up with the actual correct velocity and acceleration. You know what I mean? With whether you're taking the derivatives or not. Like those are just the places where you put the acceleration and velocity that someone in that rotating coordinate system reports to you. But what about the position? So the position vector is that, so whenever P comes up here and here for this rotating coordinate system, is that talking about the position, the apparent, like observed position to an observer in the rotating coordinate system, or a true position vector? It doesn't matter. It's both, okay? The position vector is both the apparent position vector in the rotating coordinate system and the true position vector. And the reason for that is you're not taking any time derivatives. Remember that all the problems happen when you take derivatives of vectors. Position isn't the derivative of anything, so there's no problem there. Okay?
Could you explain that further?
Yeah.
Because if we look at it from the point of view of like the camera example that you told us yesterday, wouldn't one camera be saying no change in position as it's rotating with the person, and another saying
Yeah, so the difference comes about because, so remember there were 3 frames that I drew, right? 3 video frames. And in one of them, the position vectors look the same, and 2 of them, they look different. The 2 that look different only look different because of a change in orientation of the coordinate system. It's not because of the rotation of the coordinate system. It's just that instantaneously, one of those coordinate systems has a z-axis pointing this way and one this way. You can correct that just with a rotation matrix. That's not the problem that we're dealing with here. Okay, the difference that we're dealing with here isn't a rotation matrix thing. It's a thing that has to do with the derivatives. Okay. So I know that's confusing, but I think to me, stored in your head is like the problems that we're dealing with have to do with time derivatives in rotating coordinate systems. They don't have to do with different orientations of coordinate systems. We've dealt with that stuff before without any of this crazy stuff, you know? Like just, yeah, change the, like, the different answers that you get for a block sliding on an incline in this coordinate system versus this coordinate system, you know? That's just a change in, yeah, I mean, that's just using cosine and sine. That's different than the stuff that we're dealing with now. But this is what makes the position vectors different in those 3 examples from yesterday. Just this. Okay, and then the meaning of these other terms, you can think of capital omega dot cross P. You can think of as sort of an unobserved tangential acceleration. So the person sitting in the, so like if that astronaut chair thing is speeding up, somebody in a fixed coordinate system sees a tangential acceleration for that, okay? Someone rotating with it doesn't measure a tangential acceleration, but that's where it appears in this problem. Someone standing on the ground sees a tangential acceleration. Someone standing on the center and rotating with the astronaut doesn't measure a tangential acceleration, and this adds it in.
So it's unobserved
by the rotating coordinate system, yeah. And then the term capital omega cross P is the unobserved centripetal acceleration. And again, unobserved by the rotating coordinate system. And then the last one, that last term, that's kind of hard to make sense out of intuitively, 2 omega cross the observed velocity is called the Coriolis acceleration. In the Simpsons, they say that that's the reason that toilets in Australia rotate down the drain backwards, but apparently that's not really true. Yep, I did that wrong. Observed, yeah. Yeah, sorry about this. This one that I gave you a minute ago, I just associated that with the wrong term. So it's this funny looking term. This one's funnier looking because all the other ones you can kind of, like if you think about them enough, you can kind of make sense out of. Like they have, you know, you can tell that this is some kind of tangential acceleration. You can tell that this is some kind of centripetal acceleration, but we're not used to seeing anything that looks like this. And that one is the Coriolis acceleration. And really, like knowing the names of those things, isn't really necessary for doing problems. But if you like sort of putting intuition to the math, that's kind of why.
So what's the observed velocity?
Just the P, just the components dot. Okay, so
So then what's the omega cross T?
that is the unobserved centripetal acceleration. That's centripetal acceleration that the rotating coordinate system doesn't see and has to be added in. Any other questions about those right now? Any of these? All right, so what I want to do is I want to do that astronaut training thing and actually do the calculation and do it 3 different ways. Like one of the things, I don't know, like one of the things that I think is cool about this topic is someone was just asking me about this the other day about the problem set. Like, how do I check the answers? Like, how do I know? And really there aren't too many ways to just like general ways to check your answers. Like making yourself certain that your answer is right is usually harder than doing the calculation in the first place, you know, and it takes different approaches for different problems. But here is a case where you have multiple ways to do a problem to check your answers. Okay. So example, I like to call this problem Astronaut 3 ways. I don't know. Some are on YouTube, but I've never asked them. Okay, so here's the astronaut. Let's do one way the way that we're most comfortable with by now, and then we'll take a break and come back and do the two new ways of doing it. So let's say that we're trying to calculate the acceleration of the astronaut. Might as well calculate the force. So let's say, how did I do it before? I called this z and this y, and then x is coming out. And these are the three ways. So the first way is the coordinate system origin is at the hinge, like is drawn over here, in the orientation shown. And it doesn't rotate with the arm. Okay, so, and let's say this is 5 meters. And what's a good angular velocity for this arm? How fast would it? Maybe take 2 seconds to go around. So, and let's say it's a constant angular velocity of pi radians per second. So that's 2 seconds to go around. Okay. 2 seconds for 2 pi. All right, so that means that this coordinate system is sitting in this orientation, and only one time per rotation is the z-axis pointing right at the astronaut. Okay, like 1 second later, the astronaut's in the negative z direction. Okay. And the second approach is coordinate system origin is at the hinge. And the z-axis stays, remains pointing along the arm. Okay, so this is a rotating coordinate system. What about the coordinate system origin? Is the coordinate system origin accelerating? No, it's so let me write that here. But the origin doesn't accelerate. And then the last, any questions about either of these two? And then the last one we're going to do is a coordinate system fixed on the chair So this is number 3. So the coordinate system origin is on the chair, and the z-axis always points in the direction of the arm. So in this case, is the coordinate system, are the axes rotating? Yep. And what about the origin? Is the origin accelerating? It is, because that origin is in a circular motion around the center. Okay? So this is, in a way, this is sort of the deluxe model. This is making this problem as complicated as possible. Yeah?
Part two, you said the origin doesn't accelerate, but wouldn't the, I mean, the coordinate system is rotating, but isn't the origin rotating as well? So it's,
The origin is just a particle, and particles you don't worry about their changes in orientation. You only worry about their motion, you know. So this one, so yeah, it's all that particle is doing is changing orientation, and that's not a real thing for a particle.
Okay.
But this one is actually accelerating because it's going in a big circle. It has centripetal acceleration. That's right. Yep, that's right. Question?
I have a question.
Yeah.
What's the difference between 2 and 3? Because if the coordinate system is on the hinge, right, then it's rotating with the arm. Is that not correct? Or no?
It's rotating. So yeah, it is rotating. The axes are changing orientation. But can anyone come up with the position vector as a function of time for number 2? What's the position vector as? Well, that, let's see. So of the, okay, wait. So so the coordinate system from number 1, that's an inertial coordinate system, okay? So we're trying to come up with accelerations in this first coordinate system, basically. So now think of using the coordinate system in number 1, the one where the axes aren't rotating. What's the position vector of the origin for number 2? Okay, so now think of the origin for number 2 not as a coordinate system origin, but just as a point. Okay, and in that non-rotating coordinate system, what's the position vector of that point as a function of time? It's just 0, 0, 0. You know, like, I don't think I said that very clearly, but there's no translation. Yeah, exactly. The position vector in an inertial coordinate system is constant. So, okay, so take a different inertial coordinate system like this, you know. What's the position vector of that rotating origin? It's this, you know. And what is it 2 seconds later? It's this. It stays that. So what's the velocity? Take a time derivative of a constant vector, it's 0. What's the acceleration? 0. Take another time derivative. So there's no acceleration of this origin. What about this origin, though? This one does have a centripetal acceleration. And so, so yeah, we are going to have to use relative motion for that one. Okay, so before we take a break, let's do the warm-up problem where this coordinate system isn't rotating. So the first way. So we have an inertial coordinate system. And it's just in the orientation shown. and I guess I didn't write the problem here, but so, and what's a good mass for an astronaut? 60 kilograms. What's the net force? Now let's, instead of net force, let's say what's the force applied to the astronaut by the chair? Okay, so the astronaut's in circular motion, right? So yep. So the acceleration is equal to alpha cross r plus omega cross r. And what's the r vector? So yeah, so the vector that we want for r is going from the center of the circular motion to the point that we care about. So if I call this, I'll call this A and this B. That r is 2b from A. Okay, so this is 0 because there's no angular acceleration of the arm. So we have omega is equal to, I didn't choose a direction. Let's make it positive. Is it, what axis is that angular velocity about? Y, yep. So we have 0, pi, 0 crossed with 0, pi, 0 cross, and then what's RBA? 0, 0, 5. And so you get 0, pi, 0 crossed with 5 pi, 0, 0. And so you get 0, 0, negative 5 pi squared. Okay. So this is the stuff, you've been doing this stuff back since we did particle kinematics. Okay. This is just in the inertial coordinate system, a circular motion. And so now free body diagram. So there's the astronaut.
Why do we have no centripetal acceleration?
We do have tangential, because I said that it's a constant angular velocity.
And the reason why the angular velocity is 0, pi 0 is because the z is in the.
So just think about what axis it's rotating about. So you can think of like the y-axis is the hinge that this circle is spinning around. So always just think about what the axis is that the circular motion is happening around, and that's the axis of rotation. Yeah. Okay, so free body diagram. So there's weight, that's 60 times 9.81, so 58 point, what is that? I was, what, 86? And then there's a force vector applied to the astronaut by the chair. Okay, thanks. Yeah. And so Newton's second law says FAC plus, I guess that's in the negative y direction, the weight force, plus 0. Oh, I need to, this is a three-dimensional problem, so let's expand this. Yeah, right. 0, negative 588.60 is equal to 60 times the acceleration we just calculated. 0, 0, negative 5 pi squared. And so you get a total force vector of 0, 588.6, and then negative 300 pi squared. Can someone, what's 300 pi squared? Okay, so 0, 588.6. What did you say, 20? Okay. Negative. Okay, so you see that the big force you're dealing with, the big acceleration you're dealing with is, I guess the only acceleration in this case, is a centripetal acceleration, you know, from this thing spinning around. Any questions about that problem? So, yep.
Is there a moment present? Because that's the chair and the astronaut is fixed.
We're treating the astronaut like a particle, so no. But, and there definitely needs to be a moment between the, you know, that some motor is providing to the arm, but we're ignoring that because we're just saying we observe this motion and we don't care what's causing it. But if we treated the astronaut as a rigid body and measured lengths and stuff, you know, like this part of the chair is touching his back and this part is touching his legs, and like he's not rotating at all, then yeah, you might have to deal with some couples and things. But we're just trying to figure out the total force by treating him as a particle. So before we calculate the force, what would kill him is the acceleration. So what's 5 pi squared? 45? Oh no, he'd be fine. That's less than 5 G's. Yeah, right. Yeah. Yeah, I think you can, for short periods, I think you can, people can survive like up into the teens of G's for small numbers of seconds. I think 10 G's is, you can, like people who are trained to deal with it.
Yeah, what are the astronauts?
I don't know. I don't know, but I just remember hearing it about fighter pilots, like, oh.
Fighter pilots are trained out to 9 Gs.
Okay, yeah. Yeah, right, because apparently like any fighter jet, like you're sitting there with the power in your hands to kill yourself through acceleration. And so you have to know like what the boundary is. Like if you're going fast and you just crank, you're dead, you know? Or you're unconscious and then dead shortly after.
Yeah.
So Okay, let's take a 10-minute break, come back at 11 after 2, and we'll go through the 2 new ways of doing this that should give us the same answers. That's our goal.